So finite automata are often drawn as graphs, and it's a great way often a good way to represent them. So first off, we're going to have three states. So I have a state labeled 0, I'll have a state labeled 1, and I'll have a state labeled 2. Trying to think where to best to put this. I'll put this one over here. Okay. Uh, the start state I'm going to represent with by putting a little arrow into it that comes from nowhere, and that's just to indicate that it's a start state. Any accepting states, I'm going to represent that in my graph by putting a double wall around it. Okay, that's a bit ugly. Try that again. Okay, so we'll have a double shell on accepting states. The alphabet doesn't really get shown on the picture, but the transitions do, and usually the alphabet is obvious from the labels on the transitions. Uh, so what are our transitions? Our first transition, we have a transition from 0 to 1. So I'll represent that with an arrow or an edge going from 0 to 1. And the label on that is the length 1 string with just an A in it. Okay? I'll just put an A. I won't put the square brackets around it or anything. You know that it's a string. Okay? So that's one. That was one transition. Our second transition here goes from 1 to 1, and it's labeled with a B. So we can represent that with an arrow from state 1 to state 1. Okay, and I'll label that with a B. We have an arrow from state 1 to state 2 labeled with a C. And we also have another transition from 1 to 2, and this one's labeled with an epsilon. Okay, that is an empty string. Not the symbol epsilon, but an actual empty string. So all my labels are either strings of length 0 or length 1. Okay? This arrow up here, that's not a transition. It's just a little marker to indicate that this is the start state. Right? Okay. So this is our edge label directed multigraph. It's directed because the edges have directions. It's a multigraph because we can have multiple edges between the same two nodes going in the same direction. That makes it a multigraph. Now, what does it mean? Well, so just as we gave a meaning to a regular expression by defining what language it corresponds to, we're also going to give a meaning to um, our NDFRs by defining what a language that they define. Okay, and in fact, I'm going to do more than that. I'm going to for each state in my NDFR, I am going to assign a language. Okay, and then the language of the NDFR will be the language of its start state. Okay. And we're going to, there's a couple of ways you can do this. I kind of like, I'm going to show you both ways. The first way is an inductive definition. We're going to give you rules by which you can determine that certain strings are in the language of certain states, and you can apply these rules again and again and again any finite number of times to prove that a string is in a state. And if there is such a way to do that proof, then the string is in the state, and if there's no such proof, then the string is not in the language of the state. I think I said the string is in the state. What I meant is the string is in the language of the state. Let's look at our definition and our example at the same time. And I apologize for my handwriting. It's going to be particularly bad here. We're going to have language of state 0. We're going to have a language, this is for automaton A. Let's suppose our example here, did I call that A? Yeah, I called that A. So, so we have language 0, language of state 0. We have language of state 1. And we'll have the language for automaton A of state 2. Okay? Okay. So I'm going to build these up bit by bit. They're, I think, some of them are infinite, so I won't list the whole thing, but I'll list enough strings that you get the idea. Okay, let's look at our inductive definition. The first rule says that if Q is a final state, then epsilon is in the language of Q. Well, in our example, we have one final state, and that's 2, so epsilon will be in the language, that is the empty string, is in the language of state 2. Maybe some other things too, we will see. In fact, actually there won't be, so I don't need that comma. All right, and then our second rule says that if there's a transition QRS and the string T is in the language of the destination state, the target state, then S catenated with T, remember S comes from the label, that will be in the language of the source state. Okay? So using what we know so far, which is only that epsilon is in this language of state 2, what can I learn? Well, because of this transition here, I can learn that epsilon catenated with epsilon is in the language of state 1, and that's epsilon. So language of state 1 includes epsilon. And then from this transition, I can learn that because, let's see, here we have a C on the label, so I catenate C with epsilon. The epsilon comes from being in the language of state 2. And so the string that just contains a C, that string is going to be in the language of state 1. Okay? What else can I learn? Well, I have no transitions coming out of state 2, and so I can't use this rule to learn about any more strings in the language of state 2. And that means there aren't any, because there's no more rules. There's just these two rules. So actually, state 2 is finished. State 1, we can do more here. Let's do some more work on state 1. There's also this transition that goes into state, that comes out of state 1. It also goes into state 1. And using that together with what we already know about state 1, I can add some more strings. So I could take B from the transition and catenate with epsilon that I already know is in state 1. And then I know that B is in the language of state 1. Similarly, I could take B, and then I know that C is in the language of state 1, so that tells me that catenating those two strings together, I get B, C. That's in the language. And then, again, I could take this transition and the fact that I know that B is in the language of this state, and I get that BB is in the language. Okay. Let's see, also, now using that transition yet again, I can see that BBC will be in the language, okay? And so on. So I won't write that down. But BBC and BBB and BBBC and BBBB and so on. These will all be in the language, okay? So language of state 1 is infinite. And then language of state 0, um, well, again, I just need to look at the transitions that come out of state 0. And there's this one here. There's only one. And so what this tells me is I can put an A in front of any member of the language of state 1, and I get an item that's in the language of state 0. So I'm going to get A. Okay. And we'll get ABB, and we'll get ABBC and ABBB and ABBBC and ABBB and so on ad infinitum. So you can see that the language of, well, okay, so, the last thing we have is we have this meta rule, which is that a string is in a language only if we can show it using a finite number of applications of these two rules. And I think you can see that there's really nothing new to be seen. So, other than for this example, other than what I've described, and that's because I've used every final state and I've looked at every transition and used it to generate as many strings as possible. Okay. Okay. Now the language of the whole automaton, and in the I called this automaton A. Automata don't have to be called A, but this one is. So the language described by the automaton is the language described by its start state, and you can see we could also describe that with a regular expression. So we have an A followed by any number of B's, followed optionally by a C. Okay. Remember the superscript question mark was a way of saying that something is optional. Okay, and that's a regular expression, so I'll underline it.